Welcome back to Mechanical Engineering Made Simple. If two solid steel spheres collided anything faster than a casual walking pace, like literally just 1 foot per second, they permanently dent each other.
Yeah, the physics of impact are incredibly unforgiving.
Right. It's so violent that the math governing our static, predictable world just completely unravels in a matter of milliseconds. We spend, well, most of our time engineering for equilibrium.
Exactly. We want the bridge to stand still. We want the machine casing to hold its shape.
But today, our mission for this deep dive into the sources is to explore what happens during that microscopic window of pure chaos when two bodies actually slam together.
It's a fascinating shift in perspective.
It really is. So whether you are designing heavy machinery or, I don't know, investigating a structural failure or just trying to figure out why your phone screen shattered when it fell off the table, you have to understand the invisible violence of an impact.
And I like that we're building this up as an escalation today, because an impact isn't just a force being applied. It's a profound, rapid disruption of a system.
We'll start with the perfect mathematical illusion of a clean bounce and then gradually turn up the speed until the equations literally break down and the material shatters.
That's the perfect roadmap. Because when you generate massive impulse-type forces at a tiny point of contact for just a fraction of a second, you send a shock wave of complexity through the material.
Which is wild to think about.
Right. And our understanding of how to handle that complexity has evolved. We've gone from treating objects like indestructible billiard balls to recognizing them as highly volatile, vibrating webs of energy.
Let's start at that baseline, though. The perfect billiard ball scenario. Before we can understand how massive steel structures bend and vibrate, we have to look at the classic direct central impact between two rigid spheres.
Yes. The sources immediately point us back to Isaac Newton for this one.
Good old Newton.
Always, right. He made this fundamental experimental observation. He noticed that when two bodies collide, their relative velocity after they bounce off each other is in a constant ratio to their relative velocity before they hit.
They're just traveling in the opposite direction.
Exactly. And he called that constant ratio the coefficient of restitution.
Which is basically the mathematical embodiment of a material's bounce.
That's a great way to put it. And the brilliance of Newton's observation, especially when you pair it with the law of conservation of linear momentum, is that it lets us treat the actual collision like a locked black box.
Okay, this is the Blinkist level insight from the sources that I find so fascinating. Let me do some spoken math here to explain it.
Go for it.
The core equation for Newton's observation is this. You have u prime minus x prime equals negative e multiplied by the quantity u minus x.
Right, where u and x are velocities before the impact.
Yeah, and the primes are the velocities after. And then you bring in the conservation of linear momentum, which is, let me get this right, m sub u times u prime plus m sub x times x prime equals m sub u times u plus m sub x times x. So basically, if we know the masses of the two spheres, and we know exactly how fast they were moving before they hit each other, we can map out the velocities after the crash without ever having to calculate the messy details.
Without knowing anything about the force during the split second they touch.
Yeah, you just check the entry and exit receipts. We don't actually need to know what happens inside the black box.
It is the ultimate cheat code in classical mechanics. Because, trying to map out a specific reference to the force of contact as a function of time during a high-speed collision.
I'm guessing it's a nightmare.
Oh, it requires horrific, calculus-heavy time integrations. The forces are spiking, the geometry is warping. It's a mess.
But by relying on energy and momentum, you bypass the microscopic violence entirely.
Completely deducible from what went in.
Which perfectly explains the classic ballistic pendulum experiment. If you want to know the muzzle velocity of a bullet, you don't try to mathematically model the bullet, literally tearing its way through wood fibers in real time.
No, that would be practically impossible.
Right. You fire the bullet into a heavy block of wood hanging from a string, let it embed, and just measure the final velocity of the swinging block.
You work backward from the resulting swing. Using the conservation of momentum, you find out how fast that bullet was traveling when it left the barrel.
It's beautifully elegant.
It is, but as with all simplifications in engineering, it carries severe limitations. The ballistic pendulum only works because the bullet embeds itself, and we can conveniently ignore the internal vibrations of the woodblock.
But what happens when things actually bounce? Like what is physically happening at the exact microscopic point of contact between two supposedly solid spheres?
Well, that's the catch. Nothing in the real world is perfectly rigid. At the microscopic level, even the hardest steel spheres squish when they hit each other.
They deform.
Yeah, and that squish forces us to abandon the simple rigid body illusion. This is where we have to introduce the Hertz theory of impact.
Heinrich Hertz.
Right. Hertz decided to look at the relation between the total pressure being applied and the displacements at the point of contact. He wanted to measure what he called the relative approach.
The relative approach of the centers of the spheres, basically how much they compress into one another.
Exactly.
The sources mention that Hertz found this relative approach varies as the 2/3 power of the total pressure. Let's pause on that for a second. Why the 2/3 power?
It's a very specific number.
Yeah. What is the physical mechanism behind that specific nonlinear number?
Well, it comes down to the geometry of a sphere. Think about when two perfectly flat plates press together. The contact area stays the same, right?
Right, so the pressure grows linearly.
But when a sphere presses into a flat surface or into another sphere, it starts with an infinitely small point of contact.
Oh, I see.
And as it squishes deeper, that circular flattened contact area expands outward nonlinearly. Because the area distributing the force is constantly growing wider the deeper you push, the relationship between the pressure and the compression follows that 2/3 power rule.
Okay, geometrically that makes perfect sense. But I have to push back on the core premise of Hertz's theory here.
Oh, what caught your eye?
I read through this section in the sources twice because I was so confused. Hertz derived these formulas for the force between the spheres and the radius of that circular contact area based on bodies being pressed together under purely statical conditions.
Statical, yes.
But we are talking about a high-speed dynamic collision. Why are we modeling it using math designed for things sitting at rest being slowly squeezed together in a vise?
I know it sounds completely counterintuitive, right? You would assume the speed of the impact changes the fundamental material properties.
Exactly.
But Hertz's brilliant workaround functions perfectly under one very specific, crucial condition. The duration of the contact has to be long in comparison with the period of the fundamental mode of vibration for either sphere.
Wait, let me make sure I'm translating that correctly. If hitting the sphere is going to make it ring like a bell, that internal ringing vibration has to cycle much faster than the actual time the two objects spin physically touching each other.
That captures the physics perfectly. By making that assumption, engineers can treat the spheres as perfectly rigid bodies everywhere, except for a tiny, localized elastic spring exactly at the point of contact.
Wow.
Yeah, and to prove this actually works in the real world, the math relies on a dimensionless ratio, usually denoted by the letter R.
Which is the ratio of the maximum kinetic energy of vibration to the total kinetic energy of the spheres just before they collide.
Right. And under almost all ordinary conditions, that ratio R is an incredibly small quantity. That tells us that the collision simply doesn't excite much internal vibration in the spheres.
Ah, so because the vibration is practically non-existent, the energy of the colliding spheres remains translational.
Exactly. They compress that microscopic spring, the spring pushes back, and they bounce away. The statical assumption holds up beautifully in a dynamic event because the energy didn't get lost to internal ringing.
So the math survives the squish. That is fascinating. But that brings us to the next escalation. Real engineering rarely involves perfectly isolated spheres bouncing off each other in a vacuum,
Oh, definitely not.
We are dealing with machine parts slamming into casings. We are dealing with objects striking extended elastic structures, like plates or massive beams.
Right, and when a sphere hits a massive steel boundary, you can't ignore the vibrations anymore because the boundary can't just bounce away.
The game changes entirely. When a solid sphere hits an elastic plate, the plate acts as a vibrating body.
Yes, the kinetic and potential energies of the impact don't just translate into motion, they ripple out through the plate in the form of flexural waves.
Flexural waves. Instead of the gentle pebble in a pond analogy, trying to visualize a flexural wave in steel feels more like cracking a whip made out of solid I-beam.
That is a terrifying but very accurate visual. You are sending a massive undulation of stress traveling through a solid medium.
And the energy spreads over a circular area, growing outward from the impact point.
Which introduces a highly destructive variable into our structural designs. Because if you want that plate or beam to remain entirely elastic, meaning it absorbs a flexural wave, bounces back completely, and doesn't suffer any permanent plastic deformation, The rules are shockingly strict.
This is the 1 foot per second rule I mentioned at the very beginning.
Yes.
For a collision involving steel, striking steel under standard conditions, the impact velocity usually must be less than 1 foot per second to avoid yielding. That is barely a crawl.
It really highlights just how unbelievably concentrated the forces of impact are at that initial point of contact. This all happens before the flexural waves even have a chance to carry the load away.
Anything faster than a gentle tap, and you are creating localized plastic deformation. You permanently dent the steel.
And the engineering gets even more complex when we look at transverse impacts on damped, elastically supported beams.
Let's definitely explore that damping issue, because normally damping is the structural engineer's best friend. It drains the energy out of a vibrating system and stops the shaking.
Right, you would naturally assume heavy damping would save a machine from impact damage.
You really would.
Right.
But the sources show that the analysis of different types of damping reveals a pretty disturbing reality.
It does. There is external damping, which is like the air resistance around the beam or the shock absorbers it's mounted to. And then there is internal viscous damping, which relies on Stokes' law.
That's the resistance generated within the material itself, right? As the internal molecules essentially rub together and dissipate the vibrational energy as microscopic heat.
Spot on. But the sources point out that external damping actually loses its effectiveness incredibly fast at the higher modes of vibration.
So the high-frequency ripples racing through the steel just completely ignore the external mounts.
Basically, yes. Internal viscous damping does a better job with those higher modes. If the frequency is high enough, the internal damping can actually make the vibration aperiodic, meaning the wave just dies out without oscillating back and forth.
Okay, so that sounds good.
It does, but here's the most crucial and frankly terrifying finding for anyone designing machinery. Ordinary damping affords almost zero protection against the sharp initial rises in strain caused by the impact.
Wait, really? If the damping can't protect the structure from that initial violent spike in strain when the wave first hits, isn't that a massive red flag for fatigue failure?
It is the primary mechanism for long-term machine failure. You cannot treat a structure subjected to impacts as a simple, single degree of freedom system.
Because it's too complex.
Right. A machine part experiencing repeated strikes is subjected to a chaotic web of high-frequency flexural waves. Even if your damping kills the vibration quickly after the strike, that massive undamped strain spike in the first millisecond is doing microscopic damage.
So over thousands of cycles, those initial spikes slowly tear the material apart.
Exactly. Even if the impact is visually small and the vibration seems to vanish instantly, the true damage is happening faster than the damping can physically react.
Wow. And that is all while we are still mostly in the elastic range. Which brings us to the final escalation for this deep dive.
The scary part.
Yeah. What happens when we completely blow past that 1 foot per second limit? What happens when the velocity is so high and the force is so great that those elastic flexural waves simply cannot carry the energy away fast enough?
The material is overwhelmed. It stops vibrating elastically and it enters the plastic phase.
Meaning it permanently yields and deforms.
Yes. We start dealing with the concept of the plastic hinge, where large structural deformations occur under transverse impact. But the most fascinating aspect of this escalation is how the physics of the stress waves completely changes once you cross that yield point.
The speed limit of the material shifts. Because in an elastic material, the stress and strain are proportional, governed by Young's modulus, and the elastic stress waves travel at a known, relatively high speed.
But the sources note that when the yield point is exceeded, the slope of the stress-strain curve changes drastically. Well, the wave speed in a solid is directly tied to the stiffness of the material. In the elastic zone, the material is stiff, the curve is steep, so the wave travels incredibly fast. But the moment you hit the yield point, the material starts giving way.
The slope of that stress-strain curve flattens out.
Exactly. The stiffness plummets. And because of that, the velocity of the plastic stress waves is vastly slower than the elastic waves.
So as the strain gets indefinitely increased, the velocity of that plastic wave actually approaches zero.
The wave literally stalls out. And this leads to a phenomenon known as the critical velocity of impact.
The critical velocity.
Right. The velocity of an incoming object, say a speeding car or a runaway piece of industrial tooling, is completely independent of the material's internal wave speed. You can easily reach a point where the physical impact velocity is higher than the velocity of the plastic stress waves trying to propagate through the steel.
Think about what that actually means. The material at the point of contact is getting obliterated. But the internal warning system, The stress wave trying to travel down the beam to say, hey, we're taking a massive load, everyone share the burden, literally can't move fast enough to deliver the message.
The continuity of the material is violated. Because the stress cannot be communicated away from the impact zone, it builds up instantaneously at the point of contact, and the material simply snaps.
You get a catastrophic continuity failure before the rest of the structure even knows it's been hit.
That is exactly what happens. It's a terrifying physical reality.
So how on earth do engineers design for this? You can't track a stress wave that isn't moving, and all the complex mathematical time integrations break down completely when the material yields.
You have to abandon the micro-level wave tracking. You shift to a macro-level approach known as the energy method.
The energy method.
Yeah. Instead of trying to calculate the force at a specific millisecond, we evaluate the dynamic resistance of the material as a total budget of energy. We look at the total energy absorbed by the material through plastic deformation before it finally ruptures.
Oh, I see. It's essentially a crumple zone's calorie count. You figure out exactly how much kinetic energy the structure can digest before it dies.
That's a brilliant way to phrase it. It relies entirely on the ductility of the material, its physical ability to stretch, warp, and deform to soak up that energy.
The sources provide a fantastic classic example using a tension specimen to explain this.
Yes. Picture a standard medium steel bar, 10 inches long and half an inch in diameter.
Okay, I'm visualizing a heavy, solid metal rod.
Laboratory testing shows that this specific 10-inch bar can absorb a total of 1,000 foot-pounds of energy through plastic deformation before it necks down in the center and rips apart.
So 1,000 foot-pounds is his total energy budget.
Right. Now imagine a heavy 200-pound weight striking that bar with an initial velocity of 80 feet per second.
Oof. If we run the kinetic energy calculation on that, remembering that velocity is squared, which means speed kills far faster than mass, that 200-pound weight moving at 80 feet per second represents roughly 20,000 foot-pounds of energy.
And the bar only has a budget of 1,000 foot-pounds, so that 20,000 foot-pound impact doesn't just bend the bar, it ruptures it instantly.
That's total catastrophic failure.
But if we take a 50-pound weight and let it strike the same bar at 30 feet per second...
The mass is a quarter of the original, but more importantly, the velocity is drastically lower. The kinetic energy of that strike is only about 700 foot-pounds.
Exactly. The bar has a 1,000 foot-pound budget, and the impact only hands it a bill for 700, so the bar absorbs the energy.
It deforms plastically, it permanently stretches out, and it is ruined as a precise mechanical component. But it holds. It doesn't snap.
The energy method allows engineers to size protective structures based on these survivability budgets.
But there is a massive caveat in the sources that we have to talk about before we wrap up, the notch effect.
Oh, yes. The notch effect.
Because this entire energy budget, this idea that a 10-inch bar can safely digest 1,000 foot-pounds of energy, assumes that the entire 10-inch length of the bar is participating in the stretch. It assumes uniform yielding.
And that assumption is the critical vulnerability of the entire energy method. The theory demands material perfection.
Because if there is a single notch in that steel bar, or, say, a poorly executed butt weld halfway down, the energy doesn't distribute nicely through the crystalline structure of the metal.
It acts like a bottleneck.
Yeah, it's like a chain being only as strong as its weakest link. The impact energy hyperfocuses directly on that notch.
The bulk of the material in the specimen might actually remain totally fine. The vast majority of the 10-inch bar stays below the yield point, meaning it stays completely elastic.
But that tiny localized area right at the notch, or right at the edge of the bad weld, is suddenly forced to take on 100% of the plastic deformation required to absorb the impact.
And a fraction of an inch of steel simply does not have the physical volume to absorb 700 foot-pounds of energy. So it reaches its maximum stretch limit instantly, and the bar snaps prematurely.
The full energy absorption capacity of the overall structure never gets a chance to develop.
This is why material uniformity and rigorous quality control are absolutely paramount in any impact-resistant design. A single scratch left by a careless machinist or a single bad pass with a welding torch completely invalidates your 1,000 foot-pound energy budget.
It turns what should have been a survivable elastic bounce into a catastrophic, lethal failure.
All from a microscopic flaw.
It is wild to consider that a tiny scratch on a massive steel beam can fundamentally alter how that entire structure handles a split-second collision. We spend our days surrounded by objects in a state of quiet equilibrium. But as we push the limits building faster vehicles, denser cities, and more aggressive machinery, the invisible mathematics of a split-second collision dictate the safety of our physical world. Next time you drop your phone or hear the deafening crack of a pile driver at a construction site, think about those elastic flexural waves racing through the materials and the structural energy budgets fighting against incredible forces to keep the object whole.
It really makes you appreciate the engineering behind everyday objects.
Absolutely. Master the critical few, or the trivial many will master you. If this episode gave you a solid takeaway, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping alive.